Hey guys, welcome to my YouTube channel. My name is Ashank Singh and I am a second year computer science and engineering student of BIT Bangalore. Today, I am going to explain you about SR flip-flops as a part of my AD assignment. So, let's start. So, let's see what we are going to study in this presentation. At first is introduction, then types of flip-flops, SR flip-flops, circuit and construction, working, disadvantages, and applications of NSR flip-flops. So these are some of the topics that we are going to cover in today's presentation. Let's start. First topic is introduction. A flip-flop is an electronic circuit with two stable states that can be used to store binary data. The stored data can be changed by applying various inputs. So flip-flop is an electronic circuit which has two states. Like it has two stable states and it stores data in the form of binary digits. And the stored data can be changed by applying various inputs. Flip-flops and latches are fundamental building blocks of digital electronic systems used in computer communications and many other types of systems. They are used as data storage elements. It is the basic storage element in sequential logic. So it means that flip-flops and latches are the basic building blocks of the memories of a computers and other communication systems and the various other electronic devices. So they basically are used for making data storage elements. So the basic use of flip-flops and latches is for storing data and to provide data storage elements to computers and other communication systems. But a flip-flop is different from a latch. So in some of the cases, a flip-flop and a latch might work similarly, but they have a bit difference. So the basic difference between a latch and a flip-flop is a gating or clocking mechanism. So flip-flop is edge triggered and the latch is level triggered. Uh, so flip-flops and latches are used for the same reasons, but they are a bit different. In today's videos, we are concerned basically about the flip-flop and that too SR flip-flop. So let's move to the types of flip-flops. There are basically four types of flip-flops. The first being set and reset flip-flop, which means SR flip-flop. So the SR flip-flop is also known as set and reset flip-flop and it is also called as SR latch. The second type is JK flip-flop. So a JK flip-flop is a gated SR flip-flop having the addition of a clock input circuitry. That means that SR flip-flop, when it's added with a clock input, then it's known as JK flip-flop. The third is D flip-flop. So D in the D flip-flop adds for delay, and it is a digital electronic circuit used to delay the change of state of its own output signal until the next rising edge of a clock timing input signal occurs. The fourth type of flip-flop is the T flip-flop or the toggle flip-flop. The T flip-flop is a toggled when the set and reset inputs alternatively changed by the incoming trigger. This was a basic introduction about all the types of flip-flops that we have, but we basically need to read about set reset flip-flop or the SR flip-flop in today's lecture. SR flip-flops. So the most basic of all the bistable latches and bistable multivibrators is the set reset flip-flop or the SR flip-flop. The basic SR flip-flop is an important bistable circuit because all the other types of flip-flops are built from it. It means that SR flip-flop is the most basic type of flip-flop and it is a building block for all the other types of latches and flip-flops. That means we can use SR flip-flop to make more advanced latches and flip-flops. So we need to know about it in detail. The SR flip-flop is constructed using two cross-coupled digital NAND gates or two cross-coupled digital NOR gates. So SR flip-flop can be constructed by using NAND gates also and NOR gates also. So this cross coupled. I will talk about this term later on in the video, but for now we need to understand that a flip flop can be made by NAND gates also and NOR gates also, both the ways. Generally, SR bistables and flip flops are said to be transparent because their output change or respond immediately to changes in their inputs. Also, since they consist of digital logic gates along with feedback, SR flip flops are regarded as asynchronous sequential logic circuits. So, a flip flop has two inputs R and S and also two outputs Q and Q bar. So now let's move to the next topic, which is the construction and circuit of an SR flip-flop. The basic SR flip-flop has two inputs, S and R. S stands for set and R stands for reset. And the two outputs are Q and Q bar, with one of these outputs being the complement to the other. Then the SR flip-flop is two input, two output device. So an SR flip-flop has two inputs and two outputs. The two inputs are S and R and the two outputs are Q and Q bar, where Q and Q bar are the complements of each other. These are the two basic configurations for the asynchronous SR bistable flip-flop using either a negative input NAND gate or a positive input NOR gate. So as we talked about it earlier, we can create a flip-flop by using NAND gates also and NOR gate also. So we either need a negative input NAND gate or a positive input NOR gate to create an SR flip-flop. As you can see in this picture, here we have two NAND gates named X and Y and they form to create an SR flip-flop. On the other hand, in the second image, we have two NOR gates to create an SR flip-flop. So both the ways we can create it. Now let's move to the working of an SR flip-flop. So the working of SR flip-flop is divided into two parts. First part being a set state and the second part is known as the reset state. So let's start with the set state. It says that if the input R is at logic level 0 and input S is at logic level 1, the NAND gate Y has at least one of its input as 0, therefore its output Q bar must be at logic level 1 according to NAND gate principles. It means that as we can see in the image here, if we take R to be 0 and S to be 1, then the NAND gate Y has at least one of the inputs as 0. That means it has one of the inputs to be 0, and we know that if a NAND gate has one of the inputs to be 0, then it provides the output to be 1. That means here in this case for the Y NAND gate, the output, that's Q bar, becomes 1 because it has 1 0 input. And here we can also say that this Q bar is also fed back to input A, and input A is the input to the NAND gate X, and we know that Q bar is 1, so A also becomes 1. So here in this case A is also 1 and S is also 1. So for the NAND gate X, for the NAND gate X, both the inputs are the high, that both the inputs are level 1. So according to the NAND gate logic, the output comes out to be 0. So here in this case Q bar becomes 1 and Q becomes 0. This was case number 1. Now again, if we reset the input R and if the reset input R changes state and goes higher to logic 1 with S remaining high also at logic level 1, NAND gate Y inputs are now R equals to 1 and B equals to 0. Here we say that if R equals to 1 and S equals to 1, like because in the previous state it was R equals to 0 and S equals to 1. So if both R and S equals to 1, here R equals to 1 and B becomes 0 because it's taken from Q and Q is 0. So for NAND gate Y, one of the inputs becomes to be 0, and due to NAND gate logic, the y becomes the NAND output of the NAND gate y becomes 1, which is q bar, and the gains becomes high and q again becomes to the 0. So here we notice that when r equals to 1 and s equals to 1, then also q bar becomes 1 and q equals to 0, which is similar to the previous state. So there is no change in the state of the q and the q bar. Therefore we say that the flip flop is latched or set with q bar equals to 1 and q equals to 0. So this was all about the set state of a SR flip flop. Now let's move forward to the reset state of an SR flip flop. So reset state is the second stable state of an SR flip flop, where q is at logic level 0 and q bar is its complement, so it's obviously at logic level 1, and it is given by r equals to 1 and s equals to 0. So in this case, if q bar is 0 and q is at level 1, and we are given that s equals to 0 and r equals to 1, so for the x NAND gate, the input logics are 1 and 0. So because one of the logics are 0, one of the logic inputs are 0, so the output of the x NAND gate becomes 1. That means here q becomes 1 and q becomes 1. The output of the q NAND gate is input to the y NAND gate in the form of b. So b also becomes 1 and r was already 1, so both the inputs of the y NAND gate becomes high, that is equals to 1. So according to NAND gate principles, the output of y NAND gate becomes 0, so q bar becomes 0. So in the first case of the reset state, q bar becomes 0 and q becomes 1. Now let's see the second case. Here, if s now changes state to 1, within r remains at logic 1, that means if s becomes 1 and r equals to 1, q bar will still remain slow at logic level 0 and there is no change of state. Therefore the flip flop circuit reset state has also been latched, and we can define this reset set action in the following truth table, which is on the next page of the slide. So here it means that when in the initial case, when s was equals to 0 and r was equals to 1, then also the output was same, and when s equals to 1, r equals to 1, then also the output comes out to be same. So basically there is no change in the state whenever the input becomes s equals to 1 and r equals to 1, so it remains same. So again the reset state has also been latched to q bar becoming 0 and q becoming 1. Now let's move on to see the truth table. So this is the truth table that we formed by the observations by the last two slides. So here we can see that if in the set state s becoming 1, r is 0, so q becomes 0 and q bar is 1. So this is the first case, and as we saw that q bar is set to 1. Now when we change the state to 1, 1 and 1 for both s and r, that means when s equals to 1 and r equals to 1, then also the state of q bar and q becomes same. There is no change in the state of q bar and q, and it is set to be latched. In the reset state also, when s equals to 0, r equals to 1, q becomes 1 and q bar becomes 0, and we say that the reset state q bar is set to 0. But here also, when s equals to 1 and r equals to 1, the values of q bar and q does not change. There is no change in the states of q and q bar when s equals to 1 and r equals to 1. So just a minute. So we can say that when s equals to 1 and r equals to 1, the outputs of q and q bar does not depend on the value of s and r when s equals to 1 and r equals to 1. It remains same it remains same which they were in the previous state of S and R. Like here, when S was 1, R equals to 0, then there was no change, and the reset state also, when S equals to 0, R equals to 1, there is no change. That means the state S equals to 1, R equals to 1 does not change the values of Q and Q bar. Now let's move forward to the final stage where S becomes 0 and R becomes also 0. So here in this case we take S and R both to be 0. So this is actually an undesirable or an invalid condition, because when S and R both become 0, the outputs Q and Q bar become high altogether. That means the output Q and Q bar becomes high simultaneously, which is not possible. I will not say possible, but it should not happen, because Q and Q bar are complements of each other. That means Q should be like opposite of the Q bar. That means if Q was 0, Q bar should become 1, and vice versa. So they both can't be same simultaneously. So that's why the result is that the flip-flop loses control to Q and Q bar, and if the two inputs are now switched high again after this condition to logic 1, the flip-flop becomes unstable and switches to an unknown data state based upon the unbalance. That means when this condition comes, it's known as invalid condition or the invalid state, and the flip-flop loses control and becomes imbalance. It becomes unstable. So these were all the cases, or these were all the states in the working of an SR flip-flop. Now let's move forward to see some of the applications of an SR flip-flop. These are the basic building blocks that makes computer memories possible. We already talked about that SR flip-flops are the basic building blocks of the computer memories. Now the second point is, these sequential circuits are used for switching on the simple circuits which work on a set or reset mechanism. Example of such circuit where they are used in switch debounce circuit. So SR flip-flops are used in the circuits which work on a set or reset mechanism, and one such circuit is the debounce circuit. Third point, these are used for eliminating mechanical bounce of the switches present in the digital circuits. Fourth, it is also used as digital latching relay. So these were all the applications of an SR flip-flop. Now let's move forward to disadvantages. The main problem associated with these circuits is that they work on a simple 1-bit memory. So if set input is first taken as 0, then taken back to logic, and then the further change does not have any effect on logic 0 pulses of set input. Second point is, another drawback of SR flip-flop is invalid output when both the inputs are high, which is referred to as invalid state. So we just saw in the truth table that when both the inputs become to be 0, that is when both S and R becomes to be 0, the output comes out to be invalid. That is, Q and Q bar becomes 1 simultaneously. That is not feasible. So the state is known as invalid state or invalid condition. It is one of the disadvantages of the SR flip-flop. With this, we come to the end of our presentation. So this was all for today. Thank you very much for listening patiently. Hope you like it. Thank you very much.